Okay, so remember that an integral is the exact area. Oh, Jessica, by the way, you forgot to take your pen back.
How to do it?
Yep, I have it. It's wonderful. I thought about not telling you, but... Okay, so remember that an integral is the exact area, so you can use these different methods if you have a table to estimate area. So the first one is going to be a Riemann sum. Remember the integral from a to b f of x dx approximated by, and then you do a delta x times y1, delta x times y2, delta x times y3, plus dot dot dot. Okay, remember that your delta x's could be the same width, they could be differing widths. You can collapse the formula if the delta x is the same. Hopefully you remember that. We'll talk about it in a second. Okay, so remember that whether or not your function is an over or under estimate depends on two things. Depends on if your function is increasing or decreasing and which side you're using. So for this first one, if I'm increasing, okay, draw 3 increasing functions. Slice all of them into 3 pieces. Okay, and then we're going to draw one of each and just compare how the estimated area compares to the real area. So if I was doing that first one, okay, draw a left Riemann sum. That means that you're going to connect the dots from the left side across. So I'd go left side across, left side across, left side across. And then I'd be using these rectangles to estimate the area under the curve. Now for that one, will it be an over or an under estimation? Okay, it'll be under. Okay, then go to your next one. This time we're doing a right Riemann sum. So out of this first subinterval, I'm going to choose the right side, the right side, the right side. And then if I draw that area in, which side is that going to fall on? That would be over. Very good. Over estimate. Okay, for a midpoint Riemann sum, okay, this one's a little bit different. You would take the center and you would cut across at the center. So I'd be cutting across here. I'd be cutting across here. And I'd be cutting across here. And notice that on that one, it's inconclusive because you're going to have a little bit over, but then a little bit under, and those kind of cross out with each other, so it makes your estimate more accurate, but you can't tell which side it's on. So you won't know if it's over, under, you'll just have kind of an idea. And then I'm going to put right here, these guys cancel out. Okay, because part of it's too big, but part of it's too small. So it gives you a more accurate estimate, you just don't know which side your value's on. Okay, basic same sketch with a decreasing function. Okay, cut your area up into pieces. Okay, I'm just doing 3 to keep your graphs easy. Okay, if I'm doing a left Riemann sum, you would start on the left side and kind of stair-step your way down. So you'd cut across and down, across and down, across and down. Over or under on a left for a decreasing function. Over. And then if I do a right side, you'll notice that your right side ends up cutting under. Okay, so remember that what you're comparing is the area of the rectangles to the exact area under the curve. Okay, and then for your last one, you'll notice the same thing. It still doesn't make a difference. Okay, you end up having a little bit over, a little bit under, and it kind of cancels out with each other. Okay? Alright, so 9 times out of 10, when you're doing a Riemann sum, they're going to give you a chart. But there have been a few times that they've given you a function and asked you to do it by hand. So let's say, for example, bless you, that we're doing this next example here. So it says, let f be the function 4 to x. If 4 subintervals of equal length are used, what is the value of the Riemann sum for 1 to 3? Okay, first thing that I want you to do is we're going to make a table, but we need to split 1 to 3 up into 4 subintervals. So the way that you find how wide each subinterval should be is you'll do b minus a over n. Okay, maybe you remember seeing that. Okay, but how wide is it from 1 to 3? It's 2 units. Divide that into 4 parts. What's 2 divided by 4? 2 divided by 4 would be 0.5, a half. So what you would do is you'd have 3 minus 1 over 4. That's 2 over 4. That's 0.5. That means that as I count in the table that I'm about to make, I need to use a half as my width so that I get the right number of rectangles. Okay? So we'll start with 1. Then we'll go to 1.5. 2, 2.5, and then 3. Now, it's telling me, bless you, that I need to use a left Riemann sum. Which table in my chart am I not going to actually use? The first one or the last one if it's a left Riemann sum? The last one. So at 3, I'm just going to put an X because I know I'm not going to use that one anyway. Then remember that you are plugging into these powers. Now this one comes out to be kind of tricky if you don't know how to do your roots. So if I'm doing 4, what is 4 to the 1? 4, easy. Okay, let's jump to 4 to the 2. What is 4 to the 2? 16. Those two are easy, but when you get to the decimal ones, you're going to have to think about it as a power and a root. So if I'm doing 4 to the 1.5, that's 4 to the 3 halves, right? Because 1.5 is 3 out of 2. So when I convert that, I'm going to have to convert it into the square root of 4 and then cubed. So you'd have to, because you wouldn't have had a calculator if they gave you this one. So square root of 4 is 2. 2 cubed is 8. That's what would go in the middle. Okay, then for your next one, if you want 2.5, that's the same as 4 to the 5 over 2. And then you would have to convert that back to being a whole number as well. So 5 would be your power, but then it would be a square root. So that's really 2 to the 5th, which is how much? 32. Okay, now second thing that I want you to notice is that because our delta x's are the same, we can do the shortened version of the Riemann sum. So remember, you do delta x. You don't have to write this unless you want to. But y1, y2, y3, etc. So I'm going to use that version because my delta x is always the same. How wide is each one? 0.5. And then remember, I'm only going to list out my 4 left sides. So it would be 4 plus 8 plus 16 plus 32. 4 plus 8 plus 16 plus 32. And then for me, I'd put those in even tens. So 4 and 16 add up to 20. 8 and 32 add up to 40. 20 and 30 make half of 60. Which would give us which one? 30. Now, quick question. For your answer, okay, think about 4 to the x is an increasing function. So is this an over or an underestimate?
Under.
It's an underestimate. So the real answer is actually bigger than 30. So you'll notice all their answers are on the other side. So if you calculated that integral, you would get it wrong. Okay, because they're giving you a method. All right, turn the page. One more here. Go ahead and set up your Riemann sum. Okay, it says the table above gives select values for a continuous function. If f is increasing, which could be the value from 0 to 2? Okay, so first question that I have is, if we know f is increasing, okay, it tells us that it's increasing, and I want to know which one could be the value. Here's what I would do. Do a left Riemann sum. Is that going to be too big or too small if f is increasing? Too small. Then do a right Riemann sum. What's that going to be? Too big. Then if I want to know which of those could be the right answer, where does my right answer have to be? Somewhere between whatever the left and the right Riemann sums come out to be. Does that make sense? So do a left Riemann sum. Do a right Riemann sum. And then your real answer has to be somewhere between those two. Okay? So go ahead and set it up for me. Same delta x or changing delta x? Okay, the same each time. What is it? 0.5. And then you're adding up each of the left sides. So that'd be 6, 14, 24, and 28. And then set up your right Riemann sum. So left came out to be 36. Okay, your right one would be 0.5, 14 plus 24, plus 28 plus 34. Okay, that came out to be 50. So looking at your answer choices, okay, and I didn't write it down, but you'd just be skipping the first one and doing the last four. Which is the only one that falls between those? It would have to be B. So if they ask you which one could be and they don't give you an answer, you would have to choose a number between computing the left and the rights. Okay? If they don't tell you which side to use. So if they don't tell you a left or a right, if they're not specific, then you may have to do both and look for which answers between them. Okay? You could do a midpoint and just see which one you're closest to. That could also work. Here's the problem, is that when you, so I don't know if you guys remember talking about this, but the wider you make each of your subintervals, the less accurate your estimate becomes. So it's like, yes, midpoint might come out to be closer, but it also could come out to be not as close because you're making your intervals too wide. Your answer gets more accurate as you shrink the width of your rectangles because you're shrinking the area. So that could be another way to do it, but you may find yourself falling right between two answers. And if that happens, then I would go with one of the sides. Okay? All right, trapezoidal, integral a to b. F of x dx is approximated by, remember that these are giving you estimates of area, not the actual area. You would do 1/2 y1 plus y2 delta x plus 1/2 y2 plus y3 delta x plus 1/2 y3 plus y4 delta x plus ... Now remember, you would only do that long version if your trapezoids don't have the same delta x. If they do have the same delta x, you can pull the 1/2 and the delta x out of all of the terms. So I'm going to put or here. You would do 1/2 delta x, and then remember that you'd add y1 once, but all the other ones would be counted y twice, until you get to the very last one, would only count once. And remember, the reason why that is that your middle terms count as a left y and a right y. It's just the first ones that only count once. Okay, so we're going to do a very quick sketch of this just to talk about if it's over or under. If your graph is concave up, or if your graph is concave down. Okay, remember that that is what determines it for a trapezoidal sum. Okay, then to keep our estimate really obvious, I'm going to use only 3 partitions. Okay, but remember, the more pieces you break it up into, the more accurate your estimate's going to be. Okay, and then if I were to draw in my trapezoids, I can see that on my concave up graph, where do they fall? A little bit above. But on my concave down graph, I can see that they fall a tiny bit below. So your trapezoidal sum is less than the actual area. Versus on this one, your trapezoids are greater than actual area. Okay? So remember, for Riemann sums, it's which side you're using, increasing or decreasing, but for trapezoids, you have to know concavity. Okay, go ahead and turn the page, look at the next one. Okay? Okay, next one says we want 3 equal subdivisions. Okay, this is one where you have to make your own chart. First thing I want you to do is find your delta x for me. Remember, it's b minus a over n. B minus a over n. So if I do 2 minus negative 4, I figure out how wide it is. What's 2 minus negative 4? 6 units across. Then divide into how many parts do I want? 3. Then how wide is it going to be if I do 6 divided by 3? I'll have 2 as my width. That's what my delta x will be. So set up your chart. Going from negative 4, and we're going up by 2's. So negative 4 to negative 2, negative 2 to 0, and then 0 to 2. Okay, then from there we're plugging into our equation, which you'll see here, e to the negative x over 2, kind of a random number, but we're just plugging in. Now, I may actually rewrite that like this, 1/2 e to the negative x. If you like keeping the fraction all squished together, that's fine, but you don't have to. Okay, so let's do negative 4 first. This would be 1/2 e to the negative 4. Obviously, those negatives are going to cross out. Next one will be 1/2 e to the negative 2. 1/2 e to the 0. Remember, negative 0 and 0 are the same. And then last one would be 1/2 e to the negative, and then I'm plugging in a positive 2 so the negative would stay. Okay, then I'm going to go back and turn all these double negatives into a positive. Okay, so from there, set up your trapezoidal rule. You're going to have to factor the 1/2 out to make it match one of your answers. Well, you might have to, I guess. So remember that it's 1/2 delta x, and then you're adding y1, double y2, double y3, double y4, dot, 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 and then only yn will be counted once. Where's the one? If you factor it out, then yes. Well, I thought you did, but you actually might not have to. So I have 1/2. What's my delta x? We found it earlier. My width was 2. So what's going to happen outside that bracket with the 1/2 and the 2? They're going to cancel. So then I'll have 1/2 e to the 4th, 1/2 e to the 2, 1/2 e to the 0, which is weird that they don't just change it into a 1, but if you look at the examples, they left e to the 0 as a thing. So just you leave it 2. And then 1/2 e to the negative 2. Oh wait, and then we should have doubles on these middle ones. Double, double. Okay, now, what do you notice happens on the outside? We said we have the 1/2 from the formula, but we have the 2 from the width. Those cross out. And then in the middle, notice that if I take my 1/2 out, what I would have done is I would have wanted to cross these out. But notice that, will that match an answer if we do that? No, it won't, because look, if I cross these out, then it's like I don't have a 1/2 for these terms. So this is where multiple choice can be tricky because you just have to think about, do I want to do it this way or not? So if I take the 1/2 out, now will one of my answers match? Okay, then it would be, which one? E. Good. You don't do it on the first one or the last one because if you look at your order, you have y1 and yn only count once. Versus y2 is a base 2 and then it counts again as a base 1 for the next trapezoid. Okay, so I want you to try the next, I guess just that last one. And then we'll do some free responses. Okay? You want an Oreo?
Yes.
Okay, do it. You can do it. Okay, you're doing it. Read it. It is. Okay. You can do it. What'd you get? What'd you do? Okay, I would draw the picture and just see which one comes out. You can do it. No. Okay. Yeah, and I'll post the video. Okay, what'd you pick? C? C is correct. Okay, how does a left Riemann sum come out? Okay, that comes out to be bigger than the real value. Okay, then if I do C, that's a right Riemann sum. Okay, I'll redraw it here. Right Riemann sum is going to come out to be under the actual value. Okay, so this one is under. Okay, then a midpoint, remember we said is really accurate. And then a trapezoidal is also going to be accurate. But a trapezoidal, technically, would it be above or below? Since my graph is concave down. Where would it fall? It would fall below, but would it be more below than doing rectangles? No. So it would have been C. Now remember that A, answer choice A, is the exact area. Okay, so if we want to know which one is the least, which one is the smallest, you would have to pick rectangles on the left side because they're less accurate and they're going to be under. Okay? All right, turn the page. Okay, next one. We have two things to talk about. The first one is fundamental theorem version B. We did this a tiny bit in class. Remember, capital F of B is capital F of A plus the integral A to B. Then also remember, you could use Riemann sums when you're doing the average y value. And remember that that's 1 over B minus A integral A to B. Now, the portion of that you'd be doing for my forehead. Do I have options of where I can put it? Oh, yeah. Okay, where would I put my Riemann sum? Where would I be doing the Riemann sum? In what part? The integral part, right? That's where you would be using the Riemann sum. Okay? So take a look at your first FRQ Part A. Okay, you have a chart that has acceleration in it. In Part A, it says you want the average acceleration. This is acceleration already. We want average acceleration. Is that Formula 1 or Formula 2? That's Formula 2. So you do 1 over b minus a, integral a to b of f of x. Okay, now, what is my 1 over b minus a going to be? 1 over what? What numbers would I plug in? Okay, 0 to 6, so I do 6 minus 0. Integral 0 to 6, a of t dt. And then for this chunk right here, look, they tell you what method to use. They say to use a trapezoidal sum with the subintervals in the table. Now, do I have the same delta x or changing delta x? Same. So I'd have a 6th in the front, and then I'd have to do my trapezoidal sum. So I'd do a half delta x. What is our delta x here? What are we going up by each time? 2. And then remember, it's y1 double y2 double y3 plus y4. So it'd be 3 double 4 double 6 plus 7. Now, some stuff in there can cross out. You can do it if you want to, but you don't have to. Now, if this was average acceleration, what would your units be? They would still be meters per second squared, because remember that it's an average y value, so it should be a y value, the exact same units you already had. Okay? Go down to Part B. Says if the velocity at 0 is 11, find the approximate value of the velocity at 6, computed using a left Riemann sum with the 3 subintervals in the table. So I know the velocity at 0, that's what I have. The velocity at 0 is 11. But what do I want? The velocity at 6. And so this is a version B. So I do v of 6 equals what I have, v of 0, plus the integral from what I have to what I want. And then remember that what goes in the integral here is the derivative of what's on the outside. So if these are velocities, what's the derivative of that for me to put in here? It would be acceleration. And then notice what's in your chart, acceleration. So when you do this, this is where you're going to need to do either a Riemann sum or a trapezoidal sum. Okay, then it says here we're doing a left Riemann sum. Now for my v of 0, I already know that it's 11 plus. And then for my Riemann sum, remember there's no 1/2 in it. You're just doing the width times the lefts added up. What is my width in my table, we said? 2. And then which one is going to get skipped? 3 or 7? 7. So it'll be 2 in the front, 3 plus 4 plus 6. And 7 never gets counted because it's only a right side, it's never a left side. Okay? Now, if I were to throw in one more question on this, say I asked you if it was an over or an underestimate. Look at the values in your table. Are they going up or down? Okay, the values are going up. So if I do a left Riemann sum, where is it going to fall? Under. So the real velocity is going to be greater than whatever this value is. And so questions like that, you should anticipate those are for sure going to happen.
So you put a of t because that's the derivative of
Whatever goes inside the integral should be the derivative of what's on the outside. Okay? So this would be 4 plus 6 is 10, that's 13, double 13 is 26. So this is 37. So the real velocity is something greater than 37. You don't know exactly what it is, but you know that it's more than that. Okay? All right, turn the page for me, please.
So you know that because
because I used a left side Riemann sum on an increasing function. And you would have to know both of those two things, whether it's going up or down, given the table, and then which side you used.
So is it because that is what it is?
Mm-hmm.
It has to be.
Mm-hmm. Got it. Okay, let's see. Yeah, we can probably get through this one. Okay, so it says hot water is dripping out of a coffee maker. Fill in a large cup with coffee. The amount of coffee in the cup from 0 to 6 is a differentiable function c, where t is measured in minutes. Select values are in the table, blah, blah, blah. Okay, part C. Use a midpoint sum with 3 subintervals of equal length to find 0 to 6. Now, if I wanted to break this table up into 0 to 6, why do they only want 3 subintervals? Because I'm doing a what? A midpoint. And remember, for a midpoint, you have to skip one in the middle so that you have a midpoint available. So I'm not going to go from 0 to 1, I'm going to go from 0 to 2, and then I'm going to choose the midpoint. And then for my next one, I'm not going to go to 2 to 3, I'm going to go 2 to 4 so that I have a y value in the middle. So remember, for a midpoint, you have to skip over one of the values in your table so that that can be your height. Okay? So it would be 1/6. Okay, notice it says that here at the front, 1/6 integral. So then for my delta x, how wide is it going to be? Each of my intervals are how wide? Okay, 0 to 2, 2 to 4, 4 to 6. So it's a width of 2. And then I'm only going to add the midpoints, so it'd be 5.3, 11.2, and 13.8. Now, why is the 6 there? Because they put it there. So then it says, using correct units, explain the meaning of this. That's one of your formulas. What formula is that? Okay, I'll write it like this. What is that? That's the average value. And remember that if this is average value, it's the average of what was in your table. So what did C originally measure? The amount of coffee that was in the coffee maker. So what that stands for is the average number of ounces of coffee in the coffee maker over what period of time? From 0 till 6, and it has to be measured in minutes. So you would say that represents the average number of ounces of coffee. What are you doing? Are you trying to be like Grant in your class? Eating his snacks so loudly. Okay, represents the average number of ounces of coffee in the cup over 0 to 6 minutes. Okay, but you would have to give units, so it's measured in ounces, and then you would have to give units on your time, 0 to 6 minutes. Okay? Part E says to find C prime of 3. So C prime is a slope. So if C is measured in ounces and T is measured in minutes, what would the slope of that be measured in? Ounces per minute. Just like if it was like miles per hour, same thing. Now, what is it measuring? It'd be the rate that the coffee is dripping, right? So C prime of 3 represents the rate. Remember that a derivative is always a rate. That the hot water is dripping. Now we need to give a time, so at what time? At time t equals what? Okay, 3 minutes. And then what's it measured in? Ounces per minute. Okay? Now, it did also ask us not only to interpret the meaning, but to find it. If you have a table, how do you find the C prime of 3? What do? It has an average in it, but it's not average value. AROC, good. So C prime of 3 is going to be estimated by the average rate of change, and then what interval puts 3 inside it? From 2 till 4. And you would want to get 3 between them so that you can find the average slope around it. So I would do the number of coffee at 4, C of 4, minus C of 2, over 4 minus 2. How much coffee was there in the pot at 4? We said 12.8. Minus the amount of coffee at 2 is 8.8. And then 4 minus 2 on the bottom is 2. Now, usually on the AP test, they'll say using correct units. So remember, we said on top we'd have ounces, and on bottom we'd have minutes. Okay? All right, 2 more parts left, and then we're done. Must there have been a time when the amount of coffee was at 10? Yes or no? Yes. Which interval? 2 to 3. So we would say yes. IVT guarantees this because 2 things have to be true. One of them is the obvious one. The number you want has to be in the middle. What's the other thing that has to be true about your function? Has to be continuous. Now, when I read this, it never said it was continuous. What did it say instead? It's differentiable. And if it's differentiable, what does it also have to be? Continuous. So I'm going to put because C is continuous. And then I'm going to put because it's differentiable. And 10 is between the coffee at 2, which is equal to 8.8, and the coffee at 3, which is 11.2. And so because 10 is between those y values, I know that the coffee had to hit exactly 10 because it's not allowed to skip. Okay, last part says, must there have been an instant on 2 to 4 minutes that the coffee was pouring at a rate of 2? This is mean value theorem. This is the one that everybody seems to forget. Okay, remember, for mean value theorem, it has to be differentiable. We already know it is. And if it's differentiable, whatever the average rate of change is, that slope had to happen. So the only way they can use mean value theorem correctly is if it's differentiable and the rate that they give you is also the average rate of change. So we have to find the average rate of change on 2 to 4 and see if it's equal to 2 ounces per minute. If it is, then they did it correctly. If it's not, they didn't do it correctly. Now notice we actually already set this up here, so let's just finish it. What's 12.8 minus 8.8? What's 4 divided by 2? 2. So did they pick the correct average slope? Then there has to be a slope that equals that because it says in the problem that it's differentiable. So let's just write that out to answer the question, and then we are done. So your answer would be yes. MVT, that's mean value theorem, guarantees this because C of t is differentiable and 2 ounces per minute is the average rate of change on 2 to 4 as shown in part C, or part whatever that was, E. Okay? So remember, IVT, you can't skip the Y value. MVT, you can't skip the average slope. Okay? Good job. Break. Give me your sheets and I'll sign them. And good job.
Will you be having tutoring lunch? Because I have band practice the next 2 weeks.